No, good. Ahí. Ahí. Sí.
Es el doble letra.
Ah. There it is. We're going to run the program again, but this time we have a fixed process ID. We're hijacking the getPid function, and let's see what happened. We get okay, so that's the result. Okay. So you may be wondering why that first line, which is so important, got commented. It just happens that that function, runadd function, is sometimes called directly. For example, in the OpenSSL package regression tests, and for example, in this function, which belongs to the OpenSSL API, this function loads entropy from a file, and it may happen that the content of the length of the file is shorter than the buffer, but then the whole content of the buffer is read into the entropy state, and then there we get the same warning. Well, with commenting out this line, it was all fixed. Okay, fixed. So I leave you with Luciano.
Hola, hola. Oh, yeah. Ein, zwei, drei. 1, 2, 3. My German sucks. Okay, let's go how we can explode this. As a summarize, that's the situation. We have a random number generator where we can know all the possible outputs of that random number generator. So let's see what can we do with that situation. Yes? The first scenario is with authentication. Probably was the first one was proposed by H.D. Moore. It's quite obvious, but so many of you probably are familiar with challenge authentication or power-less authentication. How many of you are familiar with these concepts? Cool. So let's. So you know, a cryptographic pair of key, you export the public key, and the magic happens. You know the magic. So let's continue. Let's suppose for a moment that this pair of key was generated by a vulnerable Debian. Yes? In that case, let's include our evil part. You know, the real hackers use console, so that's why clean interface. This hacker has problems with small interface, so big fonts for him. So that's evil part. Suppose that this part creates this pair of key in a secure way. He knows the architecture, so he runs the vulnerable PRNG generator to create all the possibilities for all the 2^15 options of the key pair generator. Those PKR is generated by random, so everything goes well. So it's trying to brute forcing, and in one moment they're gonna get the exactly clone of this option. So in this case, the server will grant the access because the evil part has the private key. Please notice that this part is not a Debian. The Debian is here, but this part trusts in the Debian weak cryptography. Yes? So this server gets a security hole just by trusting on an Ubuntu or any Debian or something like that. Yes, let's do a demo of here. I'm really bad with shell scripting, so I asked to my mom to help me. Let's first start from the beginning. Here, I have all the RSA keys for this length for SSH, for example. Yes? Okay, I give enter, so I need to wait now. This is a quite big directory because it has all the key pairs for all the PITS files. So it takes a long to list it. And my machine is, oh, there it is. Yes, as you can see, there are two pairs. The public key and the private part was generated with this PID. This means that the process ID used for generate this pair was this one, and this is just the fingerprint. Yep. This amount of keys was generated by HD Moore, but you can generate by yourself. I mean, it's not really hard. So, my mom do this script. You know, he chose a host, a random host. I don't know why that one. He chose a user. She needs to know a user. I mean, you need to brute force a user. Yeah, and ask for password-less authentication. Yes. So she simply, with each key, she tries to use it. Yeah. And she prints it because she's a really polite woman, so she prints it on the screen. It's something nice. So, start to brute forcing. Okay, maybe this can take a while, I don't know. Okay, I get worried. Oh, there it is. Should I? Oh my God. The default answer is no. Okay. So you can see how brute force, how you can get access to a server. Of course, you need to know the username. So let's think about it. We need a user, which is a popular user, which is in all systems, which has really high privilege. Okay, you choose. Let's think about some countermeasures of this. The big problem here is that this is a not Debian server. So probably the administrator of this server is losing his time laughing of Debian users instead of patching his server. So if you are a server administrator, you need to look if your server has weak public keys. Of course, if you have an anti-brute force script, that helps really good. But you need to remove all your public keys or your weak public keys. Yeah? Debian provides few scripts for do that, but you can do your own script. It's quite easy. That's public blacklisted with this information, so you can do that. If you are a Debian administrator of this kind of server, Debian includes a new option to a SSH daemon who just avoid the blacklisted authentications. Yes? So that was a Debian-specific patch to include this new option. Yes? You know, Debian-specific patch sometimes are good. So let's go to the next scenario, man in the middle. This attack was really easy. I mean, do you have any question about authentication? Yes, please. Can you have? Yes, please choose that one. Yes.
Does the user ID that you're attacking have to have set up a key pair, or can you actually be attacking a user who set up to use password-only authentication?
Well, if they're using password, they don't using asymmetric cryptography, so there is no random involved. but you can do a man-in-the-middle attack. So because you get sure that the other part is really the other part because you are using asymmetric cryptography. So let's see how can use man-in-the-middle. Yes? Well, probably most of you are familiar with certificates. How many of you are familiar with certificates? Let's avoid this. You know, the machines are really polite, so they say hello. The certificates answer with a certificate, which is a public key signed. The client just examine the certificate, looking for something. Let's leave this part. And the client challenge the server in order to be sure that this part is correctly. Yes, the server is the only owner of the private part, so the client can be sure that the server is, I don't know, Deutsche Bank, for example. Yes? So let's introduce the evil part again. The evil part gets certificate, I mean it's public, he can get it, and let's suppose that this certificate was generated in a weak way. Yes. So the public part, it's part of a guessable key pair. So the evil part tries to find a clone in the exactly way that the other attack get a clone of the private key, and the client, let's suppose that the evil part has a way to redirect all the traffic to him, and the client will challenge the evil part. The evil part can answer the challenge because he has the private key. So the heavy part here is how you redirect the traffic. Okay, let's see this way. You need to share a LAN with this client. I don't know. Nobody uses wireless connection in 21st century, so it's hard to do. You can poison DNS. You know, it's something really hard to do. Maybe you can ask to Kaminsky how to do that, but it's really, really hard. So this kind of attack is quite funny. In fact, this kind of attack provoke a problem in OpenID infrastructure, because the OpenID infrastructure works with SSL, and most of those servers have weak certificates. So you can bypass OpenID authentication with this kind of attack, combining this and the Kaminsky poisoning. Yes? So we have a man-in-the-middle scenario. Hisec.d, Hisec, my pronunciation is quite bad, so sorry. Hisec.d make a survey of servers who are vulnerable to this man-in-the-middle attack. So they get just 100,000 servers who only 5% run HTTPS. Yes? Of course, the 95 rest are vulnerable to man-in-the-middle per se, so it's not a big deal. From these 5%, they took only the signed by certificate authority, recognized certificate authority, because the self-signed certificates are vulnerable to man-in-the-middle per se. From this portion, the 3% are weak certificates because they have been building in a vulnerable Debian or Derivate. Yes? So from the beginning, from the 200,000, only 142 are vulnerable to this problem. But if we extrapolate this problem with the numbers from Netcraft, in this moment there are 24,000 weak certificates out there. It's quite an amazing number. Yes? So the problem here is that no browsers checks for revocation. Nobody checks for revocation. Well, not nobody. There is one browser who checks for revocation. Do you know which one? Internet Explorer in Windows Vista. So, if you are a Windows Vista user, you don't have this problem. You have some other problems, but not this one. There are some ways to mitigate this.